Okay, so welcome back to this next video in which we are discussing caged inositol trisphosphate. Okay, right, so we're just in the process of looking at all the different 9 optical isomers of inositol. Right, so we just drawn this one out here, which is where we've got 3 alcohol groups on one side and 3 on the other. Okay, now before I name this one, I want to draw another structure out for you because this one is complicated. It's more complicated than the others. Let me draw another picture for you, okay, because I want to make you realize something before I give you the name, because the name will look complicated, will look more complicated than all the others if we don't understand something first. Okay, so it's again going to be another optical isomer of inositol. Okay, and it's going to have 3 alcohol groups on one side and 3 alcohol groups on the other side. But now, basically, we're going to stick the alcohol group that goes back into the page away from us in between this carbon and this carbon, rather than in between this carbon and this carbon, basically. Okay, so you might say, well, surely this optical isomer you're about to draw is exactly the same as this one, but in reality it's not. And my challenge to you is try and superimpose these two on one another. You cannot do it, okay? So for instance, if I rotate this around by 60 degrees, it will not make me this molecule, okay? So if I rotate this round, I'll get these two nicely in position here, but of course I'll have this here and then this here, and that's not right, basically. So you can't turn this by rotating it into this. So these are 2 optical isomers, but you can see that they're very nicely related to each other. And how are they so related to each other? Well, they're actually enantiomers of one another, which means that they're mirror images of one another. Okay, so enantiomers are special types of optical isomers where one molecule is a mirror image of the other. So if you imagine this molecule looking at itself in the mirror, well, basically this is its reflection upside down. If we could just sort of move this upright, okay, so imagine turning this, flipping this over like a coin, okay, so flipping it over like a coin, then that's the reflection of this one, because these two will be coming out of the page. If you imagine having a mirror here and taking the reflection of that, then basically if you flip this like a coin, that's the mirror image that this molecule would see, so they are enantiomers. Right, and that is going to affect their naming, basically. So both of these molecules are called Chiro-Inositol, okay? But this form of Chiro-Inositol here is known as the L-enantiomer of Chiro-Inositol. So this is L-Chiro-Inositol. And this is the D-enantiomer of Chiro-Inositol. So this is called D-Chiro-Inositol. Okay, right. And then there is one final optical isomer of inositol. So we're nearly done now. We've done 8 of them. And that bit's the most complicated. Understanding why those 2 are different is the one which takes the most visualization. And if you're struggling to understand it, maybe try making some models which will help. It's when you wish you had one of those plastic molecule building kits that they always had in schools and which we never used because they were never helpful. The only real time that they come in useful is to try and explain optical isomerism to someone. Right, okay, so the final optical isomer of inositol is what's known as Skylo-Inositol, and this is another beautiful one. Okay, so this is again a 3 by 3 one, so 3 on one side and 3 on the other. Okay, and it's the one where you have alternating alcohol groups, basically. So you have an alcohol group coming out of the page towards us, okay, then you have an alcohol group going into the page away from us, then you have an alcohol group coming out of the page towards us, okay, then you have an alcohol group going into the page away from us, and let me just move this up a bit, okay, then you have an alcohol group coming out of the page towards us, okay, and finally you have an alcohol group going into the page away from us, like so. Okay, so this structure, which has rotational symmetry 3, is known as Skylo-Inositol. Okay, so we've now completed our discussion of the 9 different optical isomers of inositol. Now the one we're actually going to use is, where is it? Myo-Inositol, up here basically. This is the one that is used in inositol 1,4,5 trisphosphate. So let me draw out Myo-Inositol, because I'm going to draw it slightly differently from this. I'm going to draw it as though we flipped it over and rotated it a little bit, but hopefully your visualization skills will permit this. Okay, right. So here is another picture of Myo-Inositol, and I want to stress that we have not performed any chemical reactions to make it look like this. All we've done is rotated it a little bit. Okay, so basically you have these 3 alcohol groups, well, you have 4 alcohol groups on one side, and the important thing to understand is that you then have the 2 alcohol groups that are on the other side, and they have an alcohol group that's on the opposite side in between them. Okay, so I'm now drawing the 4 alcohol groups that are on one side as coming out of the page towards us, rather than going into the page away from us. Okay, right. So here are 3 of these alcohol groups that are coming out of the page towards us. Then you have an alcohol group that's going into the page away from us, and then an alcohol group that's coming out of the page towards us, and then an alcohol group that's going into the page away from us. Okay, so I hope you understand that that is Myo-Inositol. So any inositol molecule where you have 4 on one side and 2 on the other, and the 2 that are on the other have a single alcohol group that's coming out towards us in between them, basically, that's Myo-Inositol. Okay, right. So what we're now going to do is label up the carbons of the Myo-Inositol. So this carbon here is known as carbon 1. This carbon here is known as carbon 2, this carbon here as carbon 3, this carbon is carbon 4, this carbon is carbon 5, and this carbon is carbon 6, basically. So that's how you name the carbons within the Myo-Inositol ring. And now it makes sense why inositol trisphosphate is called inositol 1,4,5 trisphosphate rather than inositol 1,3,4 trisphosphate. Basically, if we now want to turn this Myo-Inositol molecule into inositol 1,4,5 trisphosphate, then what we're going to do is stick phosphate groups coming off the alcohol groups of the 1st carbon, the 4th carbon, and the 5th carbon here. Okay, so let me show you the structure of a phosphate group. So a phosphate group is like so. You have a phosphorus atom at the center. This phosphorus atom has an oxygen double bound to it, and then it has 2 alcohol groups coming off it, 1, 2. And then it also has an oxygen single bonded to it, and this oxygen has then acquired an electron from ionic means, and therefore has a negative charge. So this is the structure of a phosphate group. And basically you can produce phosphoester bonds between phosphate groups and alcohol groups. So imagine for a moment that this phosphate group here is a carbon atom rather than a phosphorus atom, okay? And what would this structure here look like? It would look like a carboxylic acid group. If this was a carbon rather than a phosphorus atom, it would look exactly like a carboxylic acid group, and basically it reacts very similar to a carboxylic acid group, and it's going to react with this alcohol group in a similar way to a esterification. So, you're going to remove the alcohol group from the phosphate group, you're going to remove the hydrogen from the alcohol group, these will combine together to make water, and you're then going to bind this oxygen to the phosphorus atom, okay? And that sort of a link is known as a phosphoester link. Okay, right, so we've seen thioesters and now we're seeing phosphoesters. And you're going to do this for the 1st, the 4th, and the 5th carbon. Okay, so over the page now I'm going to show you the structure that you overall get. So, we're now drawing out the structure of inositol 1,4,5 trisphosphate, which is also just called inositol trisphosphate for short, or even shorter, IP3, I for inositol, P for phosphate, and then the 3 because we have 3 phosphate groups. Okay, so the structure of this then, so it's based on Myo-Inositol, which is the main form of inositol that you have within cells. So let's start off by drawing the cyclohexane ring here, and then let's have the alcohol groups in their correct optical isomerism. So here's the first carbon, remember, and it has an alcohol group coming out of the page towards us. Okay, and then here's the phosphoester link to the phosphate group over here. Okay, like so. Then of the second carbon, the alcohol group is on the same side as the alcohol group of the first carbon. Okay, and we chose to draw the alcohol group of the first carbon coming out of the page towards us. Okay, then of this third carbon, the alcohol group is coming out of the page towards us, but it doesn't have any phosphate group linked to it. The alcohol group of the fourth carbon then goes into the page away from us, and it now has a phosphoester link to a phosphate group here. Okay, so there's the fourth alcohol group with its phosphate group on. And now the alcohol group of this fifth carbon then comes out of the page towards us, okay, and it is then involved in this phosphoester link to the phosphate group, which I'll show here. Okay, and then finally, the alcohol group that comes off this sixth carbon is going into the page away from us, and that does not have a phosphate group bound to it. So this is the structure of IP3, Inositol 1,4,5 Trisphosphate. Whew, that was a big discussion just to talk about that molecule. And some people, to clarify that they mean exactly this structure, will put a Myo in front there. So they will put Myo-Inositol 1,4,5 Trisphosphate. People who are being extremely proper will put Myo-Inositol 1,4,5 Trisphosphate there, because strictly speaking that is what you've got. Okay, right. So let me now talk about caged IP3 at last. So basically, caged IP3 is IP3 with an extra group stuck onto it that stops the IP3 from having, well, stops the caged IP3 from having its effect, basically. So you stick a group onto the IP3 molecule that stops it from actually doing anything within the cell. For instance, it stops it from binding to the IP3 receptor, okay? And therefore it's just a, inert molecule that you've put in. However, you can activate this molecule to the active inositol 1,4,5 trisphosphate by photolysing it, basically. So by shining light onto the caged IP3, you can cause it to break down. You can cause the extra group that you've added on to break off, and it will generate you a normal IP3 molecule, and that normal IP3 molecule will then go and activate its downstream targets, such as the IP3 receptor. So basically, this is a way of increasing the IP3 level within cells without having to activate a phosphoinositide pathway. Okay, so I'm going to give you an example of a caged IP3 molecule. Now, there are a huge number of different caged IP3 molecules. If you Google it, you can come up with, huge number of websites selling different caged IP3 molecules. But the principle is exactly the same. So I'm going to give you an example to illustrate the principle, because the best way to understand the principle is to see an example of that principle. Okay, so the example of caged IP3 that I'm going to give you is what's known as Myo-Inositol 1,4,5 trisphosphate. So we'll start off with the strict name for this molecule here, and it's just going to have an extra group stuck onto it, basically. So Myo-Inositol 1,4,5 trisphosphate, and then the extra group that it's had stuck onto it is P4, so it's off the fourth phosphate group here, so we put a P4 here, and then it's 1,2-nitrophenyl ethyl ester. Okay, so this is going to be 1 and then 2-nitrophenyl, and that should have a dash there, 2-nitrophenyl, and then ethyl ester. Okay, so let me show you the structure of this molecule, and then let me explain the logic in the name. Okay, so shall I use the structure that I've drawn there? No, I will just make a mess of it if I use that structure. I'll draw it out again, it doesn't hurt to revise. Okay, so here is our cyclohexane ring here. Then we have our alcohol group off the first carbon of the inositol ring. Okay, and this is Myo-Inositol, so it's coming out of the page towards us, or at least we're going to let it come out of the page towards us. And then it's got a phosphoester link to an alcohol group, to a phosphate group there. Okay, and then the alcohol group of the second carbon comes out of the page towards us. The alcohol group of the third carbon comes out of the page towards us. The alcohol group of the fourth carbon goes into the page away from us. Now, I'm not going to draw this complete structure yet because it's going to have something attached to this alcohol group here, so we'll discuss that in a moment. Okay, and then let me finish the fifth and sixth carbon. Okay, so off the fifth carbon you then have an oxygen coming out of the page towards us, which is linked via a phosphoester link to a phosphate group here, and then the alcohol group of the sixth carbon goes into the page away from us and has no phosphate group attached to it. Okay, so off the fourth phosphate group here, what we're going to do is attach another molecule, basically another group, and the way we're going to attach it is again by a phosphoester link. So what you would have had originally was an alcohol group of this other molecule, and it's going to link via a phosphoester link onto this phosphate group. Okay, so then you have a carbon, and I'm now breaking with the skeletal structure, but never mind. Okay, and this carbon has a methyl group coming off up here with a hydrogen like so, and then off here you'll then have a benzene ring. Okay, so this is the phenyl in the name, and then off this phenyl group you have a nitro group, so an NO2 group. Right, okay, so this is the structure of Myo-Inositol 1,4,5 trisphosphate P4,1,2 nitrophenyl ethyl ester. So the 2-nitrophenyl refers to the benzene ring with the nitro group of the second carbon of the benzene ring, because we're considering this the first carbon. Okay, now off the first carbon you then have an ethyl group here. Okay, so a 2 carbon group, so that's this bit of the name, and it's esterified via a phosphoester link onto the fourth carbon. So that's where the logic in this name is, that we've got this ethyl ester which also has 2-nitrophenyl attached to it, like so. Okay, so that's the logic in the name. Okay, now this whole group has a fancy name. It would be called more generally a photolabile group, which means a group which is liable to deteriorate, basically to break off in the presence of electromagnetic radiation, in the presence of photons. Okay, so basically you can shine light onto this caged IP3 molecule, and it will cause the photolysis of the bond between this photolabile group and this phosphate group. Okay, so electromagnetic radiation, basically, or photons, will cause the photolysis, which means the splitting apart of the photolabile group from the rest of the IP3 molecule, that will release IP3 molecules. Okay, so this is the principle of caged IP3, that it's a molecule that's modified so that it doesn't do anything. So this will not bind to IP3 receptors. Okay, you stick it into your cells, and then you have complete control about when that IP3 is released. As long as you aren't, working in broad daylight, you have complete control about when that IP3 is released. So when you shine light onto this molecule, onto your cells, of course, it will go in, it will cause the photolysis of this caged IP3 so that this photolabile group breaks off, and that will regenerate normal IP3, and this normal IP3 will then bind to the IP3 receptors. Now, why is this useful? Well, this is going to help us check that the reason that knocking out selenoprotein K causes a reduction in the calcium flux in response to activating the phosphoinositide pathway isn't due to some defect in the production of IP3, because if we stick in a certain amount of caged IP3 into control cells and also cells which have had selenoprotein K knocked out. Okay, so let's just draw this so that we can keep everything in mind. So if we have a control cell which has not had selenoprotein K knocked out, and then we have our selenoprotein K knockout here, and for short KO means knockout. Okay, and often you would call the control the wild type. Primary papers love that expression, WT rather than control. Okay, so basically if we put a fixed amount of caged IP3 into the cytoplasm of these cells, we take a set amount of caged IP3 and we put the same amount into each of these cells, then we can shine light onto these cells and the amount of IP3 that will be generated will be exactly the same in both of them. And we can then see if the effect, i.e. the reduction in calcium flux, is the same basically in the Selk knockout as it was when we were producing the IP3 via the phosphoinositide pathway rather than by the caged IP3. So basically what you find when you do this experiment is that again the calcium flux in the selenoprotein K knockout is hugely reduced basically, and reduced by the same fraction as you would expect from the original experiment. Okay, so basically what that shows us is that the effect that selenoprotein K knockouts the effect of knocking out selenoprotein K is affecting the pathway downstream of IP3 production, so it's not affecting IP3 production. The way that it's affecting calcium flux from the ER is by affecting the downstream pathway of IP3 production. So you're still producing the same amount of IP3, it's just that the effect that that IP3 is having is downstream, okay? And there's only one thing really downstream of the IP3, which is the IP3 receptor, so it seems therefore logical that somehow knocking out selenoprotein K is reducing the efficacy of the IP3 receptors. And the hypothesis is, for other experiments that they've done, that the reason for this is that when you knock out the selenoprotein K, you no longer have these DHHC6 selenoprotein K complexes, you don't palmitorylate your IP3 receptor subunits anymore. This destabilizes the IP3 receptors and their degradation occurs much quicker, so the number that you have within the ER membrane is hugely reduced. So even though you're producing the same amount of IP3, it's going to have much less effect because there are much less receptors for it to act on. Okay, so that concludes our discussion of caged IP3 and how it can be used in this particular example.